In early 2026, at Mobile World Congress in Barcelona, the world's largest telecom event, one topic dominated almost every conversation. Not smartphones, not faster downloads, but something much bigger, AI native networks, and the future of 6G. Researchers, telecom companies, and technology leaders gathered to discuss a radical idea. What if the next generation of wireless networks does not just connect devices? What if the network itself becomes intelligent? Now, before we talk about what is coming, let's be fair about where we are. 5G has genuinely impressive. It delivered 4K video streaming on the go. It brought cloud gaming to mobile devices with latency around 20 to 40 milliseconds, smooth enough for real-time play without a console. It enabled massive IoT deployments in smart city pilots, thousands of sensors communicating simultaneously, and extended broadband access to rural communities through fixed wireless connections that had never had reliable internet before. That is a real and meaningful leap forward. The engineers who built 5G deserve genuine credit. But here is the uncomfortable truth. The applications the world actually needs in the 2030s, the ones that will genuinely transform how humans live, work, and survive, 5G was never designed for them. I'm talking about true holographic telepresence, not a fat video call, but a life-size 3D person sitting across the table from you. Remote surgery you can feel. A surgeon's hands on one continent, a patient on another, with perfect real-time touch feedback. Living digital twins of entire cities. A continuously updated virtual replica of every road, every pipe, every building, every person. Swarms of robots thinking together. Hundreds of machines coordinating in real time, sharing a single distributed intelligence. These are not upgrades to existing applications. They are a completely different category of human experience. And the gap between them and 5G is not a gap in funding or coverage or engineering effort. It is a gap in fundamental physics and architectural design. So, here is the big question. If 5G is already incredibly fast, why can't it support these applications? For the past 3 decades, every single generation of wireless technology was built around the same core ambition. Go faster, carry more data. 1G gave us voice calls. 2G gave us text messages. 3G gave us the mobile internet. 4G gave us the smartphone era. 5G pushed the speeds higher and latency lower. Each generation was, at its core, a better pie. But 6G is something categorically different. Instead of simply delivering data faster, 6G is being designed from scratch as an AI-native network, where artificial intelligence is not an app running on top of the network, not a server in a distant data center processing traffic, but intelligence built directly into the architecture of the network itself at every layer, from the radio silos up. The network will no longer just carry information. It will understand it, it will learn from it, and it will act on it in real time. You can think of it like this. 5G is a fast data network. 6G will be an intelligent network. Let's discuss the fundamental reasons why 5G hits the ceiling with these applications. These are not opinions. They are hard architectural and physical limits baked into the 5G's original design. In 5G, the network is what engineers call a dumb pipe. It is insanely good at one thing: moving data from point A to point B as quickly as possible. But it has no understanding of what that data means, no ability to learn from what is flowing through it, no capacity to predict what is about to happen, no power to make decisions. All the intelligence, all the AI in a 5G world lives somewhere else, either at the device endpoint or inside a distant cloud data center. This creates the so-called last-mile intelligence gap. Here is how it plays out. A sensor detects something critical. That raw data travels to a cloud data center. An AI model processes it. A decision is made. That decision travels all the way back, and only then does something happen. For a music recommendation, that delay is trivial. Nobody cares. But for a robot that needs to react in microseconds, or a city that needs to reroute emergency services in real time, that round-trip delay is unworkable. Even small delays can create bottlenecks. For future systems like robot swarms, autonomous vehicles, or smart traffic networks, thousands of devices must coordinate almost instantly, and that requires something very different: a network that can learn, predict, and adapt continuously. But intelligence is not the only challenge. There are also fundamental physical limits. 5G's theoretical peak speed is around 20 gigabit per second. But truly immersive technologies, like photorealistic holographic communication, may require hundreds of gigabits, even terabit-level speeds. 6G research is already targeting speeds between 100 gigabits and 1 terabit per second. Now, latency. The delay between sending a signal and receiving a response. 5G's most demanding specification, called ultra-reliable low-latency communication, or URLLC, targets 1 millisecond latency. In practice, real-world end-to-end 5G latency typically runs between 5 and 15 milliseconds, and it varies unpredictably, what engineers call jitter. For streaming video, perfectly fine. But for things like remote surgery, autonomous driving, or real-time robotic control, even a few milliseconds can be too slow. For microsecond-level robot coordination, machines making split-second physical decisions together, you need latency measured not in milliseconds, but in microseconds. That is 1,000 times more demanding than 5G's best-case target. 6G aims to reduce latency to around 1/10 of a millisecond, nearly 100 times faster reaction times. 5G is a communication network. Its job is to move data between devices. That is all it does. It has no ability to sense or perceive the physical environment around it. It cannot detect a person working nearby. It cannot sense the structural vibration in a bridge. It has zero awareness of movement, objects, or environmental conditions, unless a completely separate, independent sensor system is installed, connected, and managed. In a 5G world, the network and the physical world are two separate things. The network carries information about the world, but it cannot perceive the world directly. For a city that needs to see itself in real time, for robots that need to sense the environment through the network, for autonomous systems that must understand their surroundings continuously, this is a foundational limitation that no limit of 5G engineering can fix. Future 6G networks may not only communicate, they may also sense the physical world. Using technologies like integrated sensing and communication, the network itself could detect movement, map environments, and even identify objects, turning wireless infrastructure into a giant distributed sensor system. Finally, there is the challenge of scale. Future smart cities, factories, and digital environments will involve trillions of connected devices embedded in roads, buildings, vehicles, and even human bodies. 5G can support roughly 1 million devices per square kilometers, which already sounds huge. But future environments may demand far more connections and far smarter coordination. 6G networks will use AI to understand the meaning and urgency of information, prioritizing critical data automatically. A medical alert, for example, who instantly takes priority over a smart fridge sending an update. Let's summarize the breakthroughs that set 6G apart from 5G. AI native from the ground up. This is the single most important difference, and it drives everything else. In every network generation before 6G, the network was passive infrastructure. Humans decided, configured it, and fixed it when it broke. AI was a tool sitting on top of the network. In 6G, AI is embedded directly into every layer of the network architecture: the physical radio layer, the media access control layer, the core network, and the application layer. This unlocks two capabilities that simply don't exist in 5G. Self-optimization. The network monitors its own performance continuously and reconfigures itself in real time with no human intervention required. Predictive resource allocation. The network anticipates demand before it arrives. When your autonomous vehicle approaches a complex junction, 6G has already pre-allocated the computing power and radio spectrum it will need before you get there. Terabit-class speed. 6G targets peak throughput of between 100 gigabits and 1 terabit per second, using sub-terahertz frequency bands with extremely wide channel width. That is 15 to 100 times the real-world throughput of today's 5G. 0.1 milliseconds latency. 6G targets end-to-end latency of 0.1 milliseconds. That is 100 picoseconds, with near zero jitter. Your nervous system takes approximately 70 milliseconds to process a touch signal from your fingertip to your brain. 6G responds 700 times faster than your own body. That is what makes remote touch feel real. That is what makes microsecond robot coordination possible. That is what makes the applications we are about to explore throughout this series actually work. Integrated sensing and communication. In 6G, the radio signals the network broadcasts for communication simultaneously function as sensors. The same signal that carries your data bounces off objects in the surrounding environment and returns to the base station, exactly like theta. The network's AI analyzes these reflections and builds a real-time map of movement, objects, and environmental conditions, without any additional sensor hardware whatsoever. The network does not just carry information about the world. The 6G network can see the world. Smart cities, autonomous factories, and ambient computing environments will eventually require trillions of simultaneous connections. Sensors in the roads, buildings, the air, and even the human body. 5G supports approximately 1 million connected devices per square kilometer. Impressive, until you start counting every sensor node in a genuinely smart city environment. But the deeper problem is not quantity, it is intelligence. 5G cannot prioritize meaningfully at scale. It generally does not know whether a cardiac monitor alert or a smart bin status update is more important. To 5G, they are just packets. 6G's AI layer introduces semantic communication. The network understands the meaning and urgency of every piece of data, not just the bits. It knows what matters. It acts accordingly. We are going to explore some of the most revolutionary applications that AI-native 6G could unlock. Applications that today's 5G networks were never designed to support, such as real-time digital twins and robot swarms. So, let's begin unlocking the future of AI-native 6G.